Hi, good morning to you all. Today we discuss about the design of FIR filter using windowing method. We can start with an example. Just go through this example. Here we want to design an ideal low pass filter with the frequency response HD of e raised to j omega is 1 for the range minus pi by 2 to plus pi by 2. 0 otherwise. We want to find the values of h of n. And the length of h of n is given as n is equal to 9. Here we use the Hanning window. So the window within the question itself, the window is specified and also the length of the filter. Okay, length of the filter is n is equal to 9. Then what is the step? First we want to find, first we want to plot HD of e raised to j omega. We want to plot the HD of e raised to j omega. It is mentioned that it have non-zero value within the range minus pi by 2 to plus pi by 2. Okay, when we check this plot, it is clear that it will pass all the frequencies below pi by 2. Okay, this filter will pass all the frequencies below pi by 2. So it is a low pass filter. It is a low pass filter. So that is the first step. Okay, so from the figure, it is clear that it is a low pass filter. It is also mentioned in the question also. Okay, you also must understand how to find it is a low pass filter, high pass filter, or any other filter from the frequency response. That's why I said that check the frequency response. From the frequency response, from itself it is clear that it will pass all the signal less than pi by 2. So it is a low pass filter. We can understand that. So second thing is that we want to check whether it is a linear phase or it is a zero phase. How can we do that? We can check the frequency response. In the frequency response, the phase term, that is e raised to j theta, theta will represent the phase. That term is 0. So it is a zero phase. It is a zero phase. What is the specialty of zero phase filter? The specialty of the zero phase filter is the center of symmetry is 0. Alpha is 0. With respect to origin, we have symmetric filter coefficient. That is, HD of n is symmetric with respect to 0. How can we compute HD of n? We have HD of e raised to j omega. Then apply inverse Fourier transform, you will get HD of n. So HD of n is given by HD of n is equal to 1 by 2 pi integral over minus pi to pi HD of e raised to j omega into e raised to j omega n d omega. You have the value HD of e raised to j omega, that is 1 for the range minus pi by 2 plus pi by 2, 0 otherwise. Substitute that in the equation and then go for integration. Finally, you will get HD of n is sine n pi by 2 divided by n pi. That is HD of n. Okay, we know that HD of n is symmetric with respect to origin and the length of the filter is 9. So the index values n varies from minus 4 to 4. From minus 4 to 4, we have 9 samples, including the sample at the origin. So they have total 9 samples and the center of symmetry is at the origin, that is 0. At alpha is equal to 0, that is the center of symmetry. How can you compute HD of n for the index value minus 4 to 4? We have the equation of HD of n. Substitute the index values. Okay, from varies from minus 4 to 4. You will get HD of minus 4 up to HD of 4. Then when we substitute the index values n, here when we substitute n is equal to 0, there is a limitation that you will get a 0 by 0 form. That is indeterminate form. How can we solve that? You can use, one method is that use L'Hospital rule. Here, what is the process? Here we take the differential of numerator and the differential of denominator separately. Then substitute the limit. Differentiate numerator and differentiate the denominator. Then we go for the substitution. That is the one method. Then another method is that we know that what is the limit theta tends to 0 sine theta by theta is 1. Sine theta by theta is 1. So that can be applied here. Here limit n tends to 0 sine n pi by 2 divided by n pi. Okay, it can be converted to in the form sine theta by theta. Here sine n pi by 2. So here we divide. So here we multiply. So this is in the form of this one, sine theta by theta form. This is in the form of sine theta by theta. So substitute the limit n is equal to 0. You will get limit theta. This is in the form of limit theta tends to 0, sine theta by theta. That is 1. So when we apply the limit, it become 1 by 2. So you will get the same answer, 1 by 2. Okay, HD of 0 is 1 by 2. Then we can substitute the remaining values. N varies from -4 to 4, except n is equal to 0. They have no other problem. Then another one is, it is a symmetry. So when we compute HD of n, how can you compute HD of n? Substitute n is equal to 1. N is equal to 1. 1 pi by 2 divided by n. N is 1. Here HD of 2, n is 2. N is 2 here. Then in HD of 3, n is equal to 3. Substitute n is equal to 3. In the general equation, substitute the value of n. You will get the answer. And here we know that it is a symmetric with respect to origin. So HD of 1 and HD of -1 are same. No need to compute it twice. Even if you compute it, you will get the same value. There is no problem. But you can reduce the step. Here, these are symmetric. So HD of 1 is equal to HD of -1. Like that, HD of 2 is equal to HD of -2. Like that, HD of 4 is equal to HD of -4. So you will get the values from -4 to 4 for HD of n. So, but we want to compute H of n. For that, we want to window this. We want to apply the window. You know that we are using Hanning window. You will know the function Hanning window. For Hanning window, it is a term minus 0.5, sorry, plus 0.5 plus 0.5 cos 2 pi n divided by capital N minus 1. Here, small n varies from -4 to 4. Here also, substitute the values. For n varies from -4 to 4, you will get the values. Here also, the window is also symmetric. The window is also symmetric about n is equal to 0. With respect to origin, it is symmetric. So you can get all the values, then go for the multiplication. After getting the window function, window coefficient, multiply this with HD of n. Okay, corresponding HD of n, you will get H of n. It will varies from 0 to 4. And also, it is symmetric. So -4 to 4, the same value. H of 1 is same as H of -1. H of 2 is equal to H of -2. So you will get the H of n from -4 to 4. You will get the values from -4 to 4. This is the H of n. With respect to origin, it is symmetric. Here, the origin is this point. The origin is at this point. When we plot H of n, it is clear that at the origin, the value is 0.5. With respect to origin, it is symmetric. These are the coefficients. When we check the coefficient, these are same. So these are same. So here -1, h of -1 is same as h of 1. H of -2 is same as h of 2. And h of -3 is same as h of 3. And h of -4 is same as h of 4. Okay, then we check that here h of n, it is a non-causal signal. What is the reason? It have non-zero values for n less than 0. For n less than 0, it have non-zero values. So it is a non-causal. How can we make it causal? By applying a shifting. We want to shift 4 units. By shifting 4 unit, right, you will get a causal signal. In general, we can say that we want to shift n minus 1 by 2 samples or units. Okay, here n minus 1 by 2 is 4. When we shift 4 unit, you will get the causal signal. And the causal signal is shown here. We just shift the 4 unit. Okay, this is a causal signal. Then if you want to plot its frequency response, if you want to plot the h of e raised to j omega, we know that it is from this h of n, it is clear that it is a type 1 filter. The reason is that capital N, length of the filter is n is odd and it is a symmetric. It is a symmetric and n is equal to odd. You can find its frequency response. How can you do that? We already studied that for a type 1 filter. For a type 1 filter, you will get the frequency response like this. H of e raised to j omega, frequency response of the type 1 filter is given as h of e raised to j omega is e raised to minus j alpha omega, and the remaining thing. Here, this one represent the magnitude of h of e raised to j omega, and this alpha omega minus alpha omega represent the phase. Okay, this is in the case of type 1 filter. If the length of the filter is even, the filter is type 2 filter. You can check the frequency response equation of type 2 filter. From that, you can compute the magnitude and phase separately, and also you can go for plotting this magnitude response and phase response. How can we do that? Substitute the value of omega. We substitute the value of omega ranges from 0 to 2 pi. You will get the magnitude response and phase response also. You can plot that also. Okay, these are the things. Okay, thank you.